feel the vibe.
Now, if it's not, another method that we have is what we call elimination. Elimination is another way that we want to get down to a single variable that we can solve and then put that answer back in to come up with the other variable. So if you need to write down the steps, there they are. We'll go through the steps one by one. So first, it says write each equation in the same form. So notice that in 4a, these are similar looking equations, but they're not in the same order. We want them to be in the same order. So I'm going to rewrite the second equation to match the first. 2x minus 3y equals 7. Then 5x plus 6y equals 4. So just reordering the terms. Now the second says multiply one or both equations by a constant, just a number, to create opposite coefficients for a variable. So what I want is in front of the x or the y, I want one of those to have a positive number and the other to have a negative number of that version between the two different equations. So if I look here, I'm going to look at the y's. So this is a negative 3y and this is a positive 6y. How could I make one of those numbers the same with one being positive and one being negative? If you said multiply the second equation by 2, then you'd be correct. Now, I can't just multiply the y by 2. I need to multiply the entire equation by 2. So what that gives me now is 2 times 2x is 4x, minus 3 times 2 is 6y. Sorry, minus 3y times 2 is 6y, and then 7 times 2 is 14. Now, the second equation I did not change, so I'm going to leave it the way that it was written. So now I can see that these two variables, y, have opposite coefficients. So in step 3, it says combine the two equations and solve for the remaining value. So basically, I can add the two equations. So I can take 4x plus 5x, which is 9x, negative 6y plus 6y, which is 0, so those essentially subtract out, 14 plus 4, which is 18. And now this gives me a single variable equation that I can solve for x. Finally, I want to go back to one of these two equations and use it to solve for y. So what I can do, it doesn't matter which one I use. I can take the 2 and put it back into either equation for x, and I'll solve to get y by itself. So what this would look like, this bottom equation, 6y plus 5 times 2, which is 10, equal to 4. So I would subtract the 10 from both sides. Again, 5 times 2 is just 10, so I'm subtracting 2 from both sides, or 10 from both sides. Then dividing by 6, y equals negative 1. So here we multiply the equations by sometimes both equations by the same number, sometimes an equation by or both equations by a different number to get some of those variables to cancel out when we add the equations together. Let's take a look at B. The first step, again, is to rewrite these in the same format. So notice that the y and the x in the bottom equation are on the same side. I'm going to go ahead and rewrite it to look the same here. So I'm going to add the 3y over, so plus 3y here essentially. So this is more than just reordering, but it's still an equivalent expression. 2x plus 3y equals 17. 4x minus 5y equals 12 because I did not mess with that equation. Now in this case, what I could look at is, yes, the 3 and the 5 have opposite signs, but it's not an easy multiplication necessarily to get them to be the same number. The x's is an easy multiplication. What can I get the 2 to multiply to 2 to turn it into 4? If you said 2, you'd be correct. But we don't just want a positive 4. We want a negative 4 because we want those to cancel out. So I'm going to multiply this first equation by negative 2x. So that's going to give me negative 2. So negative 2 times 2x is negative 4x. Negative 2 times 6 is, negative 2 times 3y is negative 6y. Negative 2 times 17 is negative 34. I did not change that second equation, so I'm just going to continue to rewrite it. Now, we can add these. And when we add these, what happens to the x's? If you said they cancel out, you'd be correct. So that gives me negative 11y equal to negative 22. So I'm adding the common terms, and that simplifies that expression so that now I can divide by negative 11 and come up with y equals 2. Now it's a substitution back into one of the equations to figure out x. So I'm going to use the 2x equation equals negative 3 times 2 plus 17. You could take negative 3 times 2 plus 17 in your calculator to figure out negative 3 times 2 is negative 6 plus 17 would be negative 11. Sorry, positive 11. And then divide by 2. So x equals 11 over 2. And similar to the last set of equations, I could throw these numbers back in there to check to see if they would work out. And we'd find that these would be good. Now let's take a look at C. Well, the last question I had you do the third problem by yourself. If you want to stop the video here and do the third problem by yourself, you can, but let's go ahead and do C together because C is a little bit more complicated. What we have here is fractions. So what I would do personally, because most of you guys don't really like fractions, is I would get rid of the fractions. So what can we multiply that would get rid of a 1/6 and a 1/4? Basically, what's the least common multiple of the denominators? If you said 12, you'd be correct. So both 6 and 4, you can multiply 6 to get to 12. You can multiply 4 to get to 12. So I'm going to multiply the top by 12 to get rid of the fractions. So negative 1/6 times 12 would be negative 2u. 1/4 times 12 would be 3v. And 4 times 12 is 48. Now, I'm going to do the same thing on the denominator. I'm going to get rid of the fraction before I worry about eliminating. So I'm going to multiply by 6 here. So to get rid of a 2 and a 3, I can multiply by 6. So that would give me 3u minus 4v equal to negative 66. So here we have gotten rid of the fractions, which is probably the hardest part for most people. Now I need to do the elimination method, because if I were to try to add now, I'd still end up with two variables, and so none of the variables would cancel. If I look at these, there's no quick, easy multiplication to get rid of the coefficients if I just multiply one of the equations. I could use a fraction, but instead, let's multiply both of the two equations. Let's take a look at this negative 2 and this 3. One's negative, one's positive. That's good. What number can I get them both to multiply to? If you said 6, that would be correct. So let's multiply the first equation by 3 and the second equation by 2. So if I do that, if I multiply the first equation by 3, that's going to give me, sorry, let me get rid of this line here. Multiply the first equation by 3, that's going to give me negative 6u plus 9v equal to 144. Again, you can multiply those numbers in your calculator. I'm going to multiply the bottom equation by 2, so that's going to give me 6u minus 8v equal to negative 132. So multiplying everything in the top equation by 3, everything in the bottom equation by 2. Now, what that does is it allows us to eliminate the v's, or the u's. So in this case, it wasn't just like A and B where I multiplied just the top. I multiplied both of these by different numbers so that I could now cancel out the u's. And when I do that, it actually takes the v down to a single number, which is nice. Now there's no more work. V is 12. No more work for that specific equation. Now I do want to be able to figure out what u is, so I can take one of these equations and now substitute in for v. So let's take this first one, so negative 1/6 u plus 1/4 times 12 equals 4. 1/4 times 12 is 3, so negative 1/6 u plus 3 equals 4. Subtract 3 from both sides, so negative 1/6 u equals 1. Multiply by negative 6, so u equals negative 6. There we have it. So fraction equations people often get a little bit confused on. The elimination method is nice with fraction equations because you can use a number to multiply to those equations to get rid of the fractions. Then we can work on the eliminating and then solving for variables. Okay? So those are the 4 steps that we're going to follow using the elimination method. These are our 3 basic algebraic or 3 methods that we're going to use to solve system of equations. Graphically, substitution, and elimination. Now, there are some things that come up, some inconsistencies or some issues that come up when we start graphing or solving systems of equations. Every equation that we've looked up so far has been what we call an independent equation. So let's take a look at it from a graphical perspective. All of these were linear equations. So here's a linear equation, and here's a linear equation. This could be an example of something we just solved. These 2 linear equations intersect in exactly one spot. Their slopes are different. If we looked at the lines, those 2 slopes are different. Doesn't matter what their y-intercepts are, but their slopes are different. When this is the case, it's going to have one real solution, and that's what we've looked at for all of our answers so far. Now, there are some cases that graphically may look a little bit different. So, what if we had this equation that looked like this, and then we had a secondary equation, and we could have a secondary equation that looked like this. Basically, they overlapped. So in this case, if we're talking about a line, again, remember the line format is y equals mx plus b. The slope from the first line is the same as the slope from the second line, and the y-intercept from the first line is the same as the second line. In this case, all of the numbers overlap here, so this would be all real solutions. So whatever the line is would be a solution. Any point on that line is going to be a solution to that system of equations. So it has an infinite number of solutions. We could also have what we call inconsistent equations. And so let's say we have these 2 lines. It's not perfect, but you can get the idea here that these 2 lines are parallel. So their slopes are equal, but their y-intercepts are not equal. So what do we know about 2 parallel lines if they don't have the same intercept? They never intersect. So this does not have any real solutions. So most of our equations will be independent. We'll come up with one real solution. But sometimes they'll be dependent, or sometimes they'll be inconsistent. And so let's actually take a look at what happens algebraically to show us those 3 different instances. So problem number 5 tells us to solve the systems using an algebraic method of a choice and determine the system if the system is independent, dependent, or inconsistent. So let's go ahead and take a look at 5a. Go ahead and see if you can solve for x and y in 5a. Go ahead and pause the video and solve now. Okay, hopefully you got a solution. What I'm going to use is substitution here. I'm going to use substitution because y is already by itself. Could use elimination. Elimination wouldn't be too difficult here, but this one's pretty quick if it's substitution. Negative 10x plus 35, I'm going to substitute the y. I'm going to replace it with 0.25x. And that equals negative 5. So as I simplify here, negative 10x plus 8.75x. So distributing the 35 into the 0.25 equals negative 5. Combine the like terms, so negative 1.25x equals negative 5. Divide by negative 1.25. And finally, we have that x equals 4. So here's part of our solution. And then we can take 4 back into y and substitute. And then y equals 1. So there's the other part of our solution. This would be independent. This is what we've been working on up to this point, where we come up with one answer, one value for x, one value for y. Now let's take a look at b. I'm going to solve b using substitution as well, because this one is not much more difficult here. The only thing I need to do in this first equation to substitute is divide by negative 1. So that would give me negative 6x plus 22 equals y. So if I'm going to substitute, I'm going to take this expression for y and put it into the second equation. So 3x plus 1/2 times, remember we want to put that negative 6x plus 22 in parentheses equals 11. Distribute the 1/2, so 3x minus 3x plus 11 equals 11. 3x minus 3x is 0, so this simplifies to just 11 equals 11. So this is something that's true. It's a true statement, but it doesn't tell us anything about x and y. Well, when you get into a solution process and you go through the steps algebraically and it's done correctly and you get a true statement, this means that all real solutions would be true. So we didn't actually have to find what x and y were, but they're going to be all real numbers. This would match up with the second option. This would be a dependent example algebraically. So when you come up with all real solutions, this is dependent. Another way that we could look at this is if we simplify this to rewrite for y, we would notice that they would have the same slope and the same y-intercept. Now let's go ahead and take a look at C. Solving this one algebraically, this one's not the best, but I'm going to go with substitution again. So let's go ahead and divide by 0.5 here to get y by itself. So if I divide the second equation by 0.5, that's going to give me y equals negative 1.5 divided by 0.5. You could do that in your calculator. That would be negative 3. 2 divided by 0.5, that would be 4. And now I can take this equation and substitute it back into the first one. So substitution in all three of these cases is probably quicker. If you did it using elimination, that's okay as well. So I get 1.2x plus 0.4 times negative 3x plus 4 equals 5. Again, we need to distribute, so 1.2x plus negative 1.2x plus 1.6 equals 5. What happens to the negative 1.2x and the 1.2x? They add to give you 0. So 1.6 equals 5. This is not accurate. It's actually not true. So here we come up with a false statement. This means that there are no real solutions. So for this problem, this would actually be inconsistent. Sorry, I think I spelled inconsistent incorrectly there. Let me fix that spelling. There we go. So this would be what we consider inconsistent because it does not have any real solutions. If we were to rewrite the equations, we would see that the slope is the same and the y-intercept is the same. So algebraically, if you're going through the process of solving, if you get one value for x and one value for y that works, that's independent. That's your only solution. If you get a statement that is just true, it tells you nothing about x and y, that's going to be all real solutions. That is dependent. If you get a statement that is false, that tells us that there are no real solutions. This is an inconsistent solution system for the system of equations. Now, that brings us